basically, I'm kind of putting here several runtimes. We have CRT0, so in the instance, a runtime is anything that helps the application bootstrap and start running, and C and C++ actually have some piece of thing that can be called a very thin layer of a runtime. Obviously, it doesn't provide any functionality, like code portability or sandboxing and so on. But yeah, it's there. We have CPython, which is the most common Python implementation. It doesn't have PGO because it interprets your code, so it doesn't have an actual compiler inside the runtime. Then you have the CLR, which is the Common Language Runtime by Microsoft that runs any language, too many. We have the Android runtime. They provide code portability, sandboxing, GC. They don't have PGO as far as I know because they compile ahead of time now. So basically they compile everything before they start the VM. You have HotSpot, which is the most common implementation for Java and other languages that compile to bytecode. You have V8, which is a JavaScript environment developed by Google, and you have HHVM, which is a Python environment as well. So it's also interesting to look. PHP, yes, language, yeah. Okay, so it's also interesting to look, and sometimes I look into this, what are developers doing? So basically, what are the top languages in terms of utilization? Sorry if you cannot read this, but basically this is like, I took this snapshot this week. This is the popularity of programming languages, and you can see that the top languages are usually languages that provide, or that run on top of runtimes that provide a lot of these features. So you have Python, Java, JavaScript, C#, PHP, and then in sixth place comes C and C++. And this kind of a common pattern, and you can see also on GitHub. They have the evolution of the, I think this is pull requests by programming language. You have JavaScript in first place, and Java and Python, PHP, and so on. And then you have job postings and so on, also the same thing. And TIOB, C shows up in second place, but still Java and Python come in like very top places. And it seems like programmers really like this thing of having like a lot of functionality that helps them develop applications. So usually it's a good thing. But some people are very like, they don't believe this is a good thing, and they say, okay, maybe performance is going to be the bottleneck for this whole thing, and I cannot write C, or sometimes I cannot talk about Java. Sometimes I'm talking about, okay, let's implement this thing in Java or in Scala, and people start looking in a different way, like, what are you talking about? You should implement this in C or C++ because you're not going to get good performance. And sometimes I get bored with this, and I just put like a very quick example, like I want to grab quicksort, like out of the textbook implementation of quicksort. The point is not going to be like having an optimized quicksort implementation, it's just throwing the most simple version of quicksort at the runtime and see what comes out of it in terms of performance. And we're going to compare C, Java, and Python. So basically what I did is just like run the same code. Obviously there are small syntactic changes because of the language. I compile the thing, and then I run it, and I'm sorting 4 megabytes just to see what happens. And this in Java takes close to 100 milliseconds. The first iteration takes a little bit longer because obviously we need to launch the runtime, compile code internally by the Git compiler, and so on, but it usually takes around this time. Now for GCC, who thinks that GCC or C is going to be faster than Java? Yeah?
Should be comparable.
Comparable? And it's like a lot more. What's happening? This is a stupid mistake, but is this like... Okay, so basically GCC by default doesn't give you good code. You have to actually force it to optimize. It's not by default. It should be the other way, I think. But when you put Yo3 flag, it actually produces good code. So it's just like, never forget to put the right option there. Yeah, so if you see the performance here, like 78 milliseconds compared to 97. So it's like 15% to 20%. So I would say, like, before jumping into let's do it in C or C++, really check if the language runtime is going to be your bottleneck. Because most of the time, you'll see applications that are either bottlenecked by I/O or for memory bandwidth or core or anything else that is not the runtime. But they still think that well, the runtime is going to be my bottleneck, I'm going to stay away from it.
How would you choose? How do you make the decision for you?
Well, it's always a trade-off between performance and productivity of the developer. I would say that most of the time you would start by doing like a prototype and try to see what's going to be like the main bottleneck of your application. And in most of the times, well, you can do different types of tricks, and this is always like, it really depends on the application. But I've seen, for example, companies, there is this Cassandra distributed hash table, and there is an implementation of C++ of that thing, which is ScyllaDB. I don't know if you know. So I was kind of doing an internship / collaboration with this company, and they really have tight SLAs, and in the middle of this SLA they need to do a request that goes through Cassandra, and they were having problems with GC. And one of the things that they thought was, okay, let's go for ScyllaDB. They don't have a GC, so this must be faster. It turns out that the GC was taking time because it was waiting for threads to load things from disk. So it was actually a I/O problem. And when they moved to ScyllaDB, they had exactly the same performance in terms of latency. So it really depends. You really need to see the performance of the application.
So the rule of the thumb is that unless you're doing some very specific, very heavy processing, such as image processing, your problem on JVM is with a reasonable language. It's not throughput, it's only latency.
Yeah.
So it's not going to be slow.
Yeah.
Sorry.
No, but that's true. Most GCs, if you come to me and say, okay, GC is 20% of my execution time, you're doing something wrong. This is not the current state of the art for GCs. Obviously, if you configure the heap in a bad way, this type of stuff can happen. Okay, so yeah, and Python. Well, let's not discuss Python. So Python was not
worse than I thought.
Yeah, I think I didn't do anything wrong, but I checked the code a couple of times. I think it's correct. It's just taking too long. Python was done for you to call some C implementation of sort and not to implement sort in Python. Yeah.
If you use PyPy, it's going to go down to 10,000 milliseconds, but it's still going to be 10,000.
Yeah. But PyPy, they have a cheat compiler, right?
Yeah.
So it's going to do something good. Yeah. Okay, so I tried to explain more or less why I'm interested in runtime. I think it's a very good idea. I think it's going to help a lot of developers to develop better code faster. Now I'm just going to keep going and explain a little bit the anatomy of a language runtime system. I'm going to use
performance or the trade-off between productivity of a runtime?
Not always. Sometimes it's a trade-off, but not always. So it can happen that you have a language that offers you both good productivity, and performance at the same time.
It's called Cal.
Yeah, but sometimes for like I can give you a concrete example. Either you choose Java or C++ for application. In C++, you can pull a lot more optimizations. You can have a lot more control over everything. It's going to cost you more in terms of development, probably. Unless you're doing something that is very simple and you can actually reuse a lot of things. If you're going to re-implement a real system, it's going to take a lot of time. This is in my opinion. A lot of C++ developers, it's like a love-hate relationship. They love the language because it gives you so much freedom, but at the same time, everything that you do, it's like super risky, and you can hurt their performance in different ways. Yeah, you have to get used to Rust. Rust forces the programmer to... So basically, Rust doesn't have a GC because the compiler can't do GC. But the GC is in the mind of the developer because it needs to know how to program in Rust in a way that doesn't require a GC. It's
like opinion.
Yeah, you have to convince developers to program in a way that doesn't need GC. That's my opinion on Rust. I do not program.
Classify Rust as less contemporary.
I wouldn't say that. Once you're used to thinking that same way, but for example, if you want to implement a database in Rust and I want to read fields and stuff like this is less intuitive to implement, I would say, than, for example, in Java, where you can just copy a reference or return some value from a database, a hash map in memory, for example. I don't want to talk a lot of... Yeah. I'm not fluent in Rust. I've looked at some programs. It kind of confuses me sometimes, the thing, but it might be my problem. But yeah, definitely, Rust is probably a good trade-off between productivity and performance. Yeah.
Both the
just like to add that it would do resource management, but it would handle that at compile time by verifying where the objects would lose scope and are untraceable. It would just add cost to drop it. So you pay the cost of resource management sometimes in the runtime, but there is no garbage collector that is running.
Yeah, that's right. Yeah. Okay. So, yeah, but thanks for the rest thing. It's probably one of the languages I should learn more actively to see what comes out of it. Okay, so moving on to the kind of anatomy of a runtime, I'm presenting a very high-level overview of what OpenJDK looks like, OpenJDK HotSpot. And this is I think it's a representative example because OpenJDK HotSpot is a rather mature implementation of a runtime and contains a lot of components that will be present in other runtimes as well. So in case of OpenJDK HotSpot, everything begins with a piece of bytecode. A piece of bytecode is something that gets compiled from, for example, Java. You use Java C, or you can use Scala or any other language that you can actually build to bytecode. And this bytecode is a hardware-independent code representation. It's basically a stack-based machine. Whereas, for example, in x86 you have a register machine. It's slightly different, but it's the same idea. You have instructions, you have operands, and so on. And this thing gets loaded into a class loader. It gets loaded by a class loader, and this class loader basically prepares a set of data structures in memory. For example, it loads classes, builds an abstract representation of a class, abstract representation of a method, and so on. Basically, this runtime data thing that we have there. These runtime data structures, well, they are basically the data structures that are going to help the runtime keep state of what's going on. And the most important thing I would say would be the heap. The heap is basically the piece of the memory that contains the application objects of the application. Well, sorry. Yeah. So moving on to the execution engine, we have three main things. One is the code interpreter. It basically goes through your code. It has like a big switch case for each possible bytecode, and depending on the bytecode that happens, you're going to execute some code. You have also a JIT compiler. A JIT compiler is going to transform your bytecode into native code. This is interesting because you're going to do a lot of optimizations here, and it's going to give you a good performance. There is a trade-off between using the interpreter and the JIT compiler. Usually, the interpreter has a very fast startup, meaning that you are going to start executing the application very, very fast, but the actual code execution speed is very slow, so the code is slower to execute. Whereas in the JIT compiler, it takes time to compile, but once it gets compiled, it's very fast. So in the JVM, they usually have a trade-off, and they only compile methods that are executed very, very frequently. And finally, we have the garbage collector, which is basically the implementation of CRIU. It's a component that will traverse periodically the application graph, and it will see which objects are still reachable and which objects can be discarded, and then we can compact memory just to save memory for new objects. Okay, so the GC has been studied, and there is a lot of problems when we are trying to scale the performance of the GC when you have a machine with more cores and memory. And this is currently an active problem. There's a lot of research going on, and this is actually one of the problems that I'm going to try to tackle here in this talk. Okay, so this is more or less what we have in a generational GC, which is the case of most of the GCs inside OpenJDK HotSpot. They're called generational GCs because they have two generations. They have the young generation and the old generation. The old generation has one space, which is the old space. This can be actually partitioned in memory. It doesn't have to be a contiguous space, but just for the sake of simplicity, let's assume that it's contiguous. And then you have the young generation, which has the hidden space, which is where all the objects are allocated. And then you have the survivor spaces, which are used to keep objects until they are old enough to move to the old space. What usually happens is the application is running, it instantiates, it creates objects, and these objects go into the hidden space. Let's imagine that objects are these small circles, and inside this circle it has like the number of GCs that this application has survived. Once the hidden is full, GC kicks in, traverses the object graph, and marks objects that are alive, and is able to move these objects that are alive to one of the survivor spaces. And then you go. So objects that are alive are pushed to the survivor space, and then we can happen this again, and they move to another survivor space, and eventually when an object is old enough, in this case 3, it's moved to the old space. This is most simple version of GC. Obviously there's a lot of techniques behind this, but this is the basic nature of GC, generational GCs. Now you have other GCs in OpenJDK that I think are not generational, but G1 is the default and currently uses 2 generations as well. Okay, so basically we allocated 32 objects, we did 9 objects, we did 9 copies of objects. Okay, let's do a simple example. Let's assume that you have this very simple and potentially stupid application, but it only performs 4 main things. It allocates a piece of memory, it loads some data into this memory, it processes it, don't care what's happening inside, and it pushes the memory, or it pushes the result to some data structure. Let's assume that you have 4 threads, 1 per core, for example, running this method in parallel. Each task will consume around 500 megabytes of memory. We'll have an hidden size of 2 gigs so that we can have all the working sets sitting in the young generation without having to push anything to the old space. And let's assume that in order to make this thing more interesting, that tasks can take different amount of times to execute. Okay. So this could be the task distribution along time. Horizontally we have time flowing, and vertically we have like the timeline for each thread. When the first thread finishes, I can actually try to use the pointer. Okay. When the first thread finishes task A, it needs to allocate more memory. Since we already have 4 tasks in the hidden space, in this space here, we have to do a GC, and this GC will have to copy our later on. So basically what we do is we have to copy 3 working sets, which is roughly 1.5 gigabytes of data. And we can keep on going on this example, and this can turn into pretty bad things. So basically, after 3 GCs, we copied a total of 4.5 gigabytes of memory. If you assume that you have around 20 gigabytes per second of available memory bandwidth, which is I think what we get in DDR4, GC is going to take at least 150 milliseconds just to copy data around. So, and we are still using 4 threads, 2 gigabytes of hidden space. If you try to scale a little bit this up, and let's say move to 8 threads, we're going to end up with at least 350. And this doesn't even count like traversing the object graph, doing all the other crazy stuff. It's just a copy, yeah. Just your theoretical minimum for the copy. And if you go one step beyond, like for 16 threads, we're going to end up with 750. While this might be okay for some applications, for other applications that need latency, this starts to be a real problem. And the reason behind this is that GC is a memory-bound thing, so it needs a lot of memory bandwidth. And the problem is, when we scale in modern commodity hardware, the number of cores and size of the memory is usually improving faster than the memory bandwidth between these two. So if you put a machine with a lot of cores and a lot of memory, if you don't provide enough memory bandwidth, your application is going to struggle during GC, because it needs to copy data around and you don't have enough. So you have a lot of cores that are creating a lot of garbage, but then your GC cannot copy memory around sufficiently fast. So yeah, the goal of one big chunk of my PhD was to try to reduce object copying. So I knew that object copying was causing a lot of application pauses, and I wanted to reduce this object copying around. Okay, so there are a lot of alternatives to this. You can say, okay, I can do like heap resizing. Instead of 2 gigs, I can put it smaller. You can do like task working set size. So instead of putting like 500 megabytes for each task, we can do it smaller as well. You can do object pooling, which basically boils down to implementing GC in user space, but okay. You can also do off-heap memory. There are several like software projects that use a lot of off-heap memory. Again, this is kind of re-implementing GC in user space. You can use some region-based or scope-based memory allocation, which is kind of similar to Rust, but it's not the same thing. They just can verify that the object is going out of the scope, and they don't even allocate it in a memory heap. This has the problem that if you want to support more dynamic things or more complex things where objects need to escape out of the scope of allocation, this can be trickier. You can also use concurrent GCs that are now coming up. You have C4 that has been around for a long time. You have Shenandoah that is being developed by Red Hat, and you have ZGC, which is being developed by Oracle people. But currently the overhead for, at least for Cassandra that I measured, is around 30%. It's basically a trade-off. If you want, these guys will provide you latency in the sub-millisecond area, but will give you a 30% trade-off for throughput. Okay, so basically the takeaway is avoiding massive object copying is not trivial. Some solutions work for some cases, but it's very hard to come up with a solution that works relatively well for a wide spectrum of applications. Okay, so the proposed solution is basically to allocate objects with similar lifetimes close to each other. So this is our proposed solution, and if we can get this, then it means that memory will be less fragmented because objects will tend to die in clusters, and we don't have a lot of object promoting because the GC will never have the chance to promote objects because either they are all alive or they are all dead. And as a consequence, object copying is going to get reduced. So in order to accomplish this, we are going to state an hypothesis that we are going to take advantage of, which is we are going to assume that objects allocated in the same allocation context are going to have a similar lifetime. So let me define what an allocation context is in the context of this work. An allocation context is the allocation site, basically the bytecode index, the method, the class, the package, and so on, aggregated with the class call graph state. So basically how the thread got into this piece of code. And if you go back to the previous example, it means that we are going to assume that all these buffer objects are going to live roughly the same amount of time if they are called through the exact same call graph. Okay, so in practice what this means is we are going to replace the collector that we have in OpenJDK HotSpot by two things. One collector that we implemented, well, it's basically a variant of G1, but it's a slightly different collector, coupled with a Runtime Object Lifetime Profiler, which is going to determine the lifetime of objects upon allocation. And these two things coupled, they will allow us to allocate objects in a specific space of the memory, and the memory will tend to be kind of clustered around the lifetimes of objects. So, yeah, so NG2C stands for N-generational garbage collector. It's built on top of G1. And Runtime Object Lifetime Profiler is basically the profiler that will produce this information over time. So for the rest of this talk, I will describe a little bit the profiler. I'm not going to talk about the NGDC. It was proposed a couple of years ago, and I don't have time to talk about both at the same time. Okay, so the Runtime Object Lifetime Profiler basically needs to answer one very simple question, which is how long are these objects going to live upon allocation? If I look at an allocation site, I need to understand how to answer this question. How long is going to be measured in number of garbage collection cycles, not in actual application time. And in order to answer this question, well, the profiler will have to mark objects upon their allocation. It will have to track objects that are being collected to increase their lifetime. It will have to track the context of the threads that are calling this code, and so on. This information is periodically going to be fed to the collector so that it knows when it's allocating an object, where to put this object in memory. Okay, so let's see how this works in practice. We have a method, for example, that is being executed. We are executing this new operation instruction, at bytecode I, and imagine that we have a thread stack T. We are going to combine both the allocation site and the thread stack into something that we call an allocation context. And we are going to install this allocation context in the header of the object that is being allocated. So basically in OpenJDK, in HotSpot, an object header, if you don't use compressed oops, which is kind of a requirement for our solutions, not to use compressed oops, you'll have 64-bit words for the header. Usually these 32 bits, the upper 32 bits that we are used for bias locking. What we see is that most of the time bias locking is not being used. Even if it's being used, we are not breaking the semantics. It just means that our profiling information is going to be discarded and we are not going to use it. So what it means is that we install the profiling information at the allocation time. If the object eventually gets bias locked, our information is going to get overridden and we are just not going to consider the object. So basically we have these 32 bits, it's 16 bits for the location site identifier, 16 bits for the context state, and this is installed upon the allocation of the object. We also keep some state of the actual counter for the number of objects allocated for each allocation context. We have a table that is indexed by the allocation context and has a number representing the number of objects that have survived from 0 up to n garbage collection cycles. Obviously, when we are allocating an object, we are going to increase the column that is respective to 0 garbage collection cycles survived so far. So this is when an allocation happens. When a GC happens, we are going to piggyback on the copy of this object, and we are going to increase the age or the counter that corresponds to a specific age in the same table up there. Okay, so I've talked about what happens when you have allocation, what happens when we have GC. Now, how do we track actually the thread that goes through the code? Well, we kind of wrap some profiling code around method calls. This is done during JIT time. However, this context tracking is very expensive, and we want to only do it for methods that are really important, or for calls that are really important. So let me just show you a small example of what happens. We have, for example, a method B that is being called. This is translated into this code, into this invoke virtual. This invoke virtual is going to be compiled by the JIT into this amount of assembly instructions. Actually, if we don't have any of our project, if ROLP is not like running, we only have this call here, so it's really optimized. Because this call is simple. And basically this code here is just checking if we should or shouldn't profile this method call. So if we should not profile, we are just going to avoid this addition and this subtraction. So why do we want to have this dynamically checked is because actually this addition and subtraction is quite expensive and we want to avoid it at all costs. So in order to understand if we can avoid tracking the method calls or not, we periodically check for conflicts. A conflict is basically when we have this situation. So we look into the object lifetime distribution table and we kind of plot the number of objects that survive 0 up to n garbage collection cycles. If we only have one peak, it means that, well, objects tend to live more or less around this amount of garbage collection cycles. However, the problem is that if we have multiple peaks, it means that the same allocation site is being called from different places. And for example, if this call means that, okay, I'm going to allocate this object and put it into one database, and it's going to live for hours. And in this guy, it's just a temporary thing that I'm doing some computation and I'm going to throw it away in a couple of milliseconds. So depending on how these guys are called, if the allocation happens here, it can really make a difference in terms of expected lifetime. So we want to differentiate between these two. And what we actually do is we try to understand what is the frame in the thread stack that can be the differentiator in terms of the two calls. So I'm not going to explain the algorithm behind this. It's a relatively simple algorithm, but it takes some time, and I think I'm running already out of time. But yeah, I'm super happy to discuss this if you want afterwards. Okay, so for implementation, we have a prototype of this running for OpenJDK 8. It's integrated with ng2c, which is also a GC implemented for HotSpot 8. This profiler is meant to be running in production workloads, so it's not meant to be running while we are in-house training your data set or doing anything fancy. Well, it's actually meant to be running every time. So in order to make this thing efficient, we had to do a lot of things inside the JVM to make this efficient. We had to avoid inline methods because most of these inline methods are usually short methods that contain relatively no control of the application. It's just like wrapping operations and so on. And this is a big boost in terms of performance. We have to properly handle exceptions because if we have an exception, we need to be able to update the context tracking and so on. We have to handle on-stack replacement, which is also a fancy technique that they use inside the JVM to kind of be able to JIT compile methods that are still executing. We also have to cope with that, and there is a bunch more of optimizations to make this thing work. Okay, so I have to show you some numbers. I'm going to compare the performance of our profiler compared to garbage first, which is the default currently in OpenJDK. And G2C is like the collector with handwritten annotations to actually force GC to allocate specific objects in a specific generation. And then we also have concurrent mark and sweep. We are going to use three platforms: Cassandra, which is a key value store. We use YCSB to generate workloads. We have Lucene, which is an in-memory indexing tool. We have read and write transactions on top of a Wikipedia dump. We have GraphG, the graph processing engine. We are going to use a Twitter graph dump to run PageRank and connected components. Okay, sorry if you cannot, well, I have some numbers on top of this. Yeah. Okay, so yeah, I have to improve the resolution of this. Okay, so this is post time percentiles. This is like what is the percentile of your pod? It means that the 50th percentile, 50% of your pods are below the value that we have here. And in the y-axis, it's represented in milliseconds, and we are comparing ROLP, which is the NG2C collector plus the profiler, and NG2C, which is collector with annotations. We have G1, which is the default, and we have concurrent mark and sweep. And these numbers represent the performance improvement compared to G1, which is the default. So two main things is, one thing is that we can approximate very well the NG2C with handwritten. So we actually spend a lot of time studying the code and understanding what is the lifetime for each line of code and how to deal with it. So we can approximate it relatively well using an automatic approach, which is good. And the second thing is that the performance or the tail latency reduction that we see compared to garbage first is relatively good. So is at least 50% and up to 85% in the case of PageRank. We also have the same data but shown in a different way, which is basically using buckets. So you can basically hide bad results if you have a lot more pauses here, but less pauses here, and still your percentile is going to look very good, although you have a lot more pauses. So this is just to show, okay, we are not making anything super bad. Essentially, we are moving pauses to the left, which is a bucket with a smaller duration in pause times, and actually not having very high number of pauses, which is good. Okay, so for throughput, so nothing comes for free, obviously. We have up to 6% of throughput overhead compared to garbage first, which I don't think is a very big problem compared to the reductions in pause time. I would say that the interesting plot here is also the ZGC. So ZGC was something that I did more recently, some tests. ZGC is a new GC that is being developed by Oracle. They use concurrent compaction, so they have really, really low pause times. Problem is that they have a higher throughput penalty that is associated with it. Also happens with C4. We also did some tests in the past with C4. And also with Chanedoa also has the same problems. For the max memory utilizations, you see that ZGC will use much more memory because it tends to use more memory just to avoid trying to catch up with the application. And for our solution, we use a little bit more memory just because since we don't trigger GCs so often, we can kind of delay a little bit and actually use a little bit more memory. Yeah. Okay, so just to wrap up, well, big data applications can definitely suffer from long tail latency problems, and I think a lot of people in the industry and Oracle and other developers from other runtimes are understanding this problem now. We're trying to take advantage of a hypothesis that seems to make sense, and we seem to get good results out of it. And this solution that we provide, a ROP or NG2C, is a prototype, but is like a drop-in replacement. You can just drop a new JVM with this thing enabled. It works as a flag in the launch time, and it will start profiling your application. Eventually, it starts making good calls and starts allocating objects in some location in the heap that gets clustered around with objects with a similar lifetime. So, yeah, I think that's it for my talk. Thanks, and if you have any questions.
Any questions? So I wonder what do you think about the goals of
Yes. Well, they have low pauses, but it costs a lot of throughput as well. So they have a relatively similar approach to these ZGC guys. So actually they have also read barriers, so they can concurrently, well, they don't compact the memory, sorry. They do not compact the memory, but they need to be sure that the application is not dirtying memory in a rate that they cannot catch up. So they will artificially limit the throughput of the application if the application starts dirtying a lot of memory.
They block it.
Yes. Yeah. They will tend to do it. I don't know the journals, but I remember I saw a talk last year, and it is actually the case. If your application is very aggressive, memory-wise, like allocating a lot and putting a lot of stuff there, actually the GC will kick in and kind of throttle down your application while it's cleaning up the memory. Something like this will happen.
Right, and I mean, that kind of makes sense. And then all the other GCs, you're going to just trigger GC more often as well and spend significantly more time in GC.
Yeah. Yes, and there is another big difference, which is they don't compact the heap. Right. So basically, over time, you'll suffer from fragmentation, which is also a problem in C++. So a lot of people seem to not realize that allocating memory in C is expensive because you have to find like good places, and after some time, it gets really challenging. So yeah, I think it's also a real problem in C++. Yeah.
And how easy is it to try?
How is it to try it out? Well, first of all, this is a prototype. Sometimes I receive an email saying, I want to use this. No, it's not completely stable, for sure. You can try it out. I'm actually going, so this is actually going to be presented next week or in 2 weeks in ETHZ. I have to make the code available in GitHub. It's going to be there, so you can actually build the JVM and try this. But again, this is a prototype. I do not guarantee this is not going to blow your face. But yeah. Right.
I mean, there's a website.
Yeah. Have my email.
Working at least, not sure, living in the Systems Group. And if you have more questions, I will do it around a little bit later on, and maybe any other day, I guess. At least weekday. So let's go. Rodrigo again.
Okay, thank you.